this lecture is going to mostly review. I use many of the same slides for this lecture as I do for 220, so I just want to make you aware of that. And so as you can see, we're going to discuss membrane potential. We've got 3 outcomes for this lecture. So just to start off, it's important to remember that ions have a charge, and this charge can be positive, negative, or even neutral in some cases. Since ions are on either side of the membrane, there's almost always going to be a difference in charge between the two sides. Membrane potential is simply the difference in charge between the inside and outside of the cell. And this value can be calculated by taking the charge on the inside of the cell and subtracting the charge from the outside of the cell. For example, if the charge inside the cell is +5 and the charge outside of the cell is -10, well, 5 minus -10 equals 15. So that would mean, in that case, the membrane potential would be +15. Now, since ions are able to cross the membrane potential is able to change. So just to remind you, there is more sodium outside of the cell than inside, and more potassium inside the cell than outside. And that's why we've got big sodium or big font on the outside and a big font for potassium on the inside. Now, based on the differences in ion concentration, there really isn't a difference in charge. However, if you remember, we've got the sodium-potassium ATPase pump. And that pump takes out 3 sodium every time it works right here, and it brings back 2 potassium every time it works. Okay? And so every time it does this, it's essentially adding a negative ion inside the cell. Okay? So we pump more charge, pump more charge, pump more charge. Okay? And so you get the idea here. And this might, just based on the pump, this might give us a hypothetical membrane potential of -10. Okay? This is not the number that you need to know. Now, inside the cell, there are negatively charged proteins. Now, despite the fact that there is a huge concentration gradient, proteins can't move outside of the cell because they're gigantic. Think of trying to get an elephant into one of your professor's offices. It's not going to happen because they don't have a big enough door. And so just the fact that we've got proteins on the inside of the cell will make the membrane potential more negative. Okay? And so now, we had a couple charges, maybe we're at -20. Again, not a number you need to remember. Next, we have 2 types of leak channels. One type of leak channel that exists is a potassium leak channel. This allows potassium to travel down its gradient. Since there is more potassium inside of the cell than outside, potassium is going to leave the cell. Every time it does this, it's like a negative charge is added to the inside of the cell. And so we do this a bunch of times, and now that -20 might become a -80. However, it's important to know that most of these potassium ions are immediately pumped back into the cell. Similar to the potassium leak channels, there are sodium leak channels. However, sodium enters the cell because there's more sodium outside of the cell. Every time a sodium ion goes inside the cell, it's like we are adding a positive charge inside of the cell or a negative charge on the outside. And so this will cause membrane potential to become less negative, resulting in a membrane potential of -70, and that's the number you need to know. However, it's also important to remember that just like potassium being pumped back into the cell, the pump also takes sodium and puts it back where it came from. In other words, nearly as fast as sodium goes inside the cell, it is pumped out by the pump. So, talking about the pump brings potassium ions in and takes the sodium ions out. Okay, now this pump requires energy. Okay, and like I said, it pulls out that sodium that is left through the leak channels. It brings the potassium back in that's left through its leak channels. And so what this does is the pump establishes the gradient for both ions. Without the pump, there would be no gradient because both of these ions would move until there are equal concentrations on both sides, which would be terrible for reasons we'll discuss later. Ultimately, the pump is what produces that negative membrane potential in neurons. So what happens if we don't have the pump? Well, it's arguably the most important aspect of the 4 contributors to membrane potential, that being the pump, the proteins, and each of the leak channels. Without the pump, there wouldn't be a gradient between the inside and outside of the cell, and this would mean that when additional ion channels open, there wouldn't be any ion movement. This means we wouldn't have any action potentials and therefore no information would be sent along. In other words, this would be very bad, and it's likely why nearly half of the energy of our brain that's used to run our brain, at least this is what we estimate, goes to running the sodium-potassium ATPase pump. So to see if you understand membrane potential, are you able to answer these three questions? Can you define membrane potential? Can you identify the four factors that establish membrane potential and explain how each of them affect membrane potential? And can you describe the sodium-potassium ATPase pump and explain its importance?